What's going on, PreCalc? Welcome to the first lesson of LMHS Online. What a momentous occasion. You are part of the very first class online. Wow. All right, we're starting off with a great one here. Graphs of polar equations. It's going to be kind of a difficult one here just to wrap your mind around. I don't think anything's going to be overly complicated. It's just that it's brand new, probably. I don't know what most of you guys have had before, but it should be pretty new. All right. We're going to be graphing them by plotting points. We're going to be using symmetry to kind of save ourselves some time. You can usually cut your graphing in half and then just flip it over. Use zeros and maximum R values to help sketch the graphs of some polar equations. And then we're going to try to be able to recognize special polar graphs that will help us save some time just by knowing some of those characteristics of some of those common special ones. Then you only have to look for like certain points in order to graph it. All right, we have learned to sketch graphs on rectangular coordinate systems, and when you did that, you began with basic point plotting. Then you used sketching aids such as symmetry, intercepts, asymptotes, periods, and shifts to further investigate those graphs. This section approaches curve sketching on the polar coordinate system, beginning with basic point plotting. All right, just basic point plotting. So our very first one. All right, if you need to sketch this out, if you haven't printed this off at home, now would be a good time to push pause and then resume whenever you're ready to go here. Okay, so the top row is our theta, what we're putting in for the angle, and your R is the length of your radius. So at 0, we're at 0, no big deal. Pi over 6, we're at 2. How far out do we get to go? 4? Can we go by halves? 2, 3, 4. No, we can't. All right, so just 2. Pi over 6, we're at 2. So here's the pi over 6 line. We go 2 rings out. 1, 2. Okay. Pi over 3, we should be at 2 radical 3, or it's about 3.5. 3.5 rings out. Looks like they're skipping pi over 4. That's too bad. 3.5 rings out. 1, 2, 3.5. Pi over 2. We are at 4 on the dot. 1, 2, 3, 4. All right, we're back to the 3.5 one here at 2 pi over 3. And then at 2 for 5 pi over 6. Pi, we're back to 0. So let's just do what we have so far. We've gone this way. We're going to keep going. Okay, at 7 pi over 6, we're at negative 2. So here's the 7 pi over 6 line, and then negative 2 means we're going to go 2 rings the opposite way. 1, 2. Now we're back to our first point. Okay, and then we're going to have negative 4. It looks like they're going to give us the next one here at negative 4. So here's the 3 pi over 2, and then negative 4, 1, 2, 3, 4. It just goes the opposite way. And you're going to see that these are going to overlap. They're going to give us another nice one here with the 2. They're not going to give us the decimal ones. They're just going to give us the nice ones. Okay, remember if it's a negative, it flips the other way. So we're at 11 pi over 6, and then negative 2 means we're going to go backwards, 1, 2. And we're going to overlap all our points. So this would end up going around twice on a 0 to 2 pi scale there. All right, so there you go. First one's done. Not too bad. Just the more you can do, and I'll even do a little bit more. I'll just go with complete overkill here and just type in every line. Do the pi over 6, the pi over 4, the pi over 3, do all of them. Okay? Just until you get the hang of it. You could confirm the graph by converting the polar equation to our rectangular form and then sketching the graph. You can also use a graphing utility and set it to polar mode and graph it. Okay? So this is just another thing that you can do with your calculator, but you're going to have to remember to change it back and forth for like other classes. Otherwise, this will mess you up. So mode, all right? We're normally in function mode, all right? And it's probably normally in degree mode as well. So you need to slide this over to radian if we're dealing with the pies, okay? And hit enter. And then we also need to change it from function over here to polar and hit enter. And then we should have a different screen for our y equals screen. And you can still do the same thing. Let's type 1 in. What did we just have there? 4 sine theta. There you go. It's probably stretched out a little bit. If you look at your calculator screen, it's a little bit rectangular, even though it's going negative 10 to 10, negative 10 to 10. It's not a square, so this is probably stretched horizontally. It's probably a little bit more circular there. And you can do trace and just type in pi over 2. Ta-da, and there you go. You can do, if you went to table, it's probably not quite as obvious because you're probably not going to know what these R values are. Or these, yeah, they're giving you whole numbers here of theta. That might be a little bit more challenging. Might just be easier to go through the trace and just type in your angles and then it goes to where it is. Could be helpful. Let's see what one of the negative ones looks like. What about 3 pi over 2? Trace 3 pi divided by 2. So I typed in 3 pi over 2, which would have been down here, but instead of telling you the R value is negative 4, it went up here to positive 4. So you're still going to have to know some things. All right. Did I skip one? I did skip one. We kind of talked about that it went around twice. It goes around twice. Note that the graph is symmetric with respect to the line pi over 2. Okay? Or what we used to know as the y-axis. It's y-axis symmetric. You could flip those over. So you can save yourself some time there. And we'll find out later some tricks for kind of just looking at the equation and recognizing what kind of symmetry it should have. Okay, symmetry with respect to the line theta equals pi over 2 is one of the 3 important types of symmetry to consider. All right, with respect to the line theta equals pi over 2, or what we used to know as the y-axis. Symmetry with respect to the polar axis, or the x-axis there. And then symmetry with respect to the pole. Remember, the pole is the origin, where we're swinging our radius around. And that is also maybe previously referred to as rotational symmetry, or origin symmetry, I guess, from back in geometry. Some tests that you can do, and you can try to remember these, but we'll even get easier than this in a little bit. That if you replace the r and theta with r and pi minus theta, or negative r and negative theta, and it comes out as the same thing, then it's going to be symmetric with that line theta equals pi over 2. Okay, if you can replace it with r comma negative theta and it works out to be the same thing, then it's going to be symmetrical with respect to the polar axis, or what we used to call the x-axis. And if you can replace it with r comma pi plus theta, or negative r comma theta, and it works out, then it would be rotational symmetry. And again, we'll get a little bit easier even than that. Okay, well, I'll cheat a little bit here for you. I'll tell you what the next one. Using the symmetry to sketch the graph of r equals 3 plus 2 cosine. Use some symmetry. Okay, I think it gives it to us one after this, or shortly after. Yeah, it kind of tells us even more shortcuts. We're just going to get to that right away. That if it's a sine, a function involving sine, remember that if you're looking at like your unit circle, sine refers to the y coordinate. So if it's a sine function, then it's going to be reflected or symmetric over the y-axis or the pi over 2 axis. Cosine would normally deal with the x-axis, so it's going to be symmetric then with the polar axis on this one. And I think that's about it. I don't have any super shortcuts for rotational symmetry for you. Okay? So we know from cosine, I'm telling you it's going to be symmetric over the polar axis, so we really only need to go 0 to pi, and then we can kind of flip things over. Okay? Like I said, I would strongly suggest a little overkill and hit all of those lines as we go here. So I'm going to hit 0, pi over 6, pi over 4, pi over 3, pi over 2. 2 pi over 3, 3 pi over 4, 5 pi over 6, and then back to pi. And then we can just reflect over. All right, so if you put 0 in there, cosine of 0 is 1, 2 times 1 is 2, 3 plus 2 that should be a 5. We'll just fill them all out and then go back and graph later. How about that? Pi over 6, you can put pi over 6 in there. This is one time. I know we're usually pretty big on exact answers. This is one time when it's okay to go with some decimals because, I mean, an exact answer is nice if it's like an answer for like a question on a test or quiz. But as far as like graphing it, a radical answer is not going to be that helpful. So this is going to be 4.7. And if you want to, actually, guys, you could just type this in if you want to see where I kind of got these points from. It's a little bit easier than just repeatedly typing it in over and over and over and over and over. 3 plus 2 cosine of theta. Nope, wrong button. Graph. All right, so we're looking for something like that. A little deflated football there, a little Tom Brady football. Deflated on that one end, a little pushed in a little bit. So we should be getting something like that. And then, like I said, how I got these is I just push trace, and then I would just type in the 0, 0, 5. Pi over 6, second pi divided by 6. This is not that helpful. They're not giving me the R values. They're still giving it to me in X and Y. Mode, radian, polar. Well, I guess that won't help then. I'm sure some of you guys are smart enough to figure out how to do that and get it to be the round one, maybe, if that's possible. Graph, trace. Theta, no R. All right, well, we're going to have to do it the old-fashioned way. And just type it in with this. 3 plus 2 cosine of pi over 6. There it is, 4.73. And then you can just hit second enter, bring it back up. Now we have pi over 4. 4.4. Pi over 3, 4. Oh, I switched pens. Pi over 2, 3. And again, with some of these guys, I would recommend maybe like doing like 4 or 5 and then graphing them, because if you go the whole thing, you might run into a situation where it flips over, and then you're not going to know like the order to connect the dots. If like it keeps switching between negative and positive, then it can get confusing on, hey, which point was that? Was that the first one or the second one? Or it gets kind of confusing on when to connect them. So yeah, 1, 2, 3, 4, 5, 4.7, just a little bit inside. 4.4, 4. Pi over 2 is at 3. So we are like this. We said this should be a little bit of a deflated football. All right. 2 pi over 3. So you're going to have to add a little space here, because we're going to have to go 2 pi divided by 3. That one's going to be a 2. Sorry, guys, I thought I had an even shorter way than this, but I guess not. 3 pi over 4. 1.6. 5 pi over 6 is going to be 1.3. And pi is going to be 1. All right, think about pi. Cosine of pi is -1 times 2 is -2 plus 3 takes it back to 1. So we got 2, and we got some fractional ones in here. Three pi over 4. I get off by 1. 2 pi over 3 was at 2. Well, that's why they're so close together. The 3 pi over 4 is at 1.6. That's 1.3. And then this one's 1. So it's really coming in sharp there. All right, then since we said it's a cosine one, so it's going to be symmetric with the polar axis, we can reflect these over. So this one can come down to here. That was 4.7. And then we had a 4.4. And then a 4. And then a 3. And then reverse this. So 1, 1.3, 1.6, 2. So it's kind of like a little heart shape almost, right? Boom, boom. All right. Fun stuff, really detail-oriented, especially when they get so close down there. Those like 1.2s, 1.3s, 1.4s on like consecutive branches there really makes it tough. The 3 tests for symmetry and polar coordinates are not, in polar coordinates are sufficient to guarantee symmetry, but they are not necessarily the only ones or the only way to go about it. For instance, we have a spiral of Archimedes. R equals theta plus 2 pi. If we graph it and look, it is symmetric with respect to pi over 2, but all the tests, individual tests would fail for it. So that's kind of a weird one. Okay. So for like the sine and cosine ones, I think it should still work out, but for like the weird ones that don't have a sine or a cosine in it, then it might not. Okay, and there's our tests. Okay, we already looked at those. And then here's the super shortcuts. This observation can be generalized to yield the following tests. If the graph of r equals some function of a sine, it's going to be symmetric with theta equals pi over 2, or your y-axis. The graph of r equals some function of cosine is going to be symmetric with respect to the polar axis. So there's the super shortcuts. They waited that long to tell you. Okay. 2 additional aids for graphing of polar equations involve knowing the theta values for which the absolute value of r is a maximum, and knowing the values for which it can be equal to 0. For instance, in example 1, the max value was 4 at pi over 2, and r equals 0 at 0. Some curves reach their zeros and maximum values at more than one point. It keeps going around, or it'll happen twice. Let's see what happens for, and again, this is another really squeezed in one. We'll see what we can use here and what isn't very usable. We have 1 minus 2 cosine of theta, so it's a cosine one, so it should be symmetric with the polar axis. So we can do 0 to pi and then flip it over. We'll see how that goes. I might go sideways here, a little more room maybe. We'll see how this works. 0, pi over 6, pi over 4, pi over 3. Okay, and again, we're going to have to sit here and just type it in over and over and over, I guess, instead of doing trace. I thought trace was going to work for us. Just keep typing it in over and over, kind of like that. We'll jump right to the chase here. 0, we should be at negative 1, negative 0.7, negative 0.4, 0, 1, 2, 2.4, 2.7, 3. Alright, some of these little ones especially might be tough to do. So at 0, we're at negative 1. So not this way, the other way. Pi over 6, we're at negative 0.7. Yeah, it's getting crowded in there quick. Pi over 4, negative 0.4. Pi over 3, we're at 0. So it's coming this way. Pi over 2, we're at 1. 2 pi over 3, we're at 2. 3 pi over 4, we have 2.4, 2.7, and 3. So we've kind of come out like this. Alright. Maybe let's reflect some of the nice ones over here. The 2.7, 2.4, 2. Alright, and we're going to have all these little itty bitty ones in there. Okay, so what it's going to do is it went like this, it's going to come back down and hit those, and then we're going to go on a little loop in here and come up and be done. This quadrant over here is going to get you negatives, and that's how it's going to flip back over there and be the reflection of those that were down there. So these really small ones, less than 1, those get tough because it gets really crowded in there. Do the best you can with those. This is not the same example 3 we did. It's a little bit different. They had 3 plus 2 cosine instead of our 1 minus 2 cosine. But you should be able to see it's the same idea. We would have gone up and around and then reflected over. Okay, 4 cosine 2 theta. So again, it's a cosine one with symmetry with the polar axis, or the x. And this is a specific one. This is going to be a 4-petal rose. So we just really need the maximums and the zeros. Think about where this would be a maximum at. This is going to be a maximum, so this is polar axis symmetry. Where would the maximum values of R be? Okay, so the maximum values for cosine are at 0 and pi. Okay, integer values of pi, and then 2 pi. Maybe you want to count it as 2 pi instead of 0. Alright, and then we're doubling it. So whatever we put in there and double it, and it comes out as an integer value of pi, then it's going to be a maximum. So what values from 0 to 2 pi could we put in there and double it? Well, if I put 0 in there and double it, it's still 0, so that's going to happen at 0. If I put pi over 2 in there and double it, it's going to come out as a pi. So pi over 2 is actually going to give me a maximum. If I put pi in there and double it, it's going to come out as a 2 pi, so that's going to happen there. 3 pi over 2 in and double it, it's going to come out as 3 pi, an integer value there. That was 3 pi over 2 would come out as an integer, and then if you did 2 pi or back to 0 again, I guess would be the same thing. It'd come out as a 4 pi. So there's our, it's going to actually happen 4 times. Normally it would happen twice. You'd get a 1 and a negative 1, but because we have this 2, we're actually going to have twice as much. So we'd have 4. Okay, think about what's going to happen here. What are those maximum values? If I put in a 0, I would get cosine of 0. Cosine of 0 is 1, and then 1 times 4 is 4. Okay. No, not all the way out there. That's not 4. 1, 2, 3, 4. Well, we can just type in pi over 6 just to see. You'll get the idea here what's going to happen. 4 times cosine 2 times pi divided by 6. We're going to have 2. And then if I do 2 times pi over 4, we get a 0. So we've gone through there. Let's do the next one, pi over 3. Two times pi over 3, negative 2. So here we are, negative 2, 1, 2. And then if I put in pi over 2, we're at negative 4. So pi over 2, we're at negative 4, which is the same thing as this way. 2, 3, 4. So we've started here, we've come around, and now we're down to here. Alright, put in 2 pi over 3. We'll do a couple of these. 2 times 2 pi divided by 3. Negative 2. And then what's the next one going to be? 3 pi over 4. Basically 0. Okay, so if I do this, I got negative 2, 1, 2. And if I do this one, I get another 0. So I've come here, I've done this little loop, back into 0. Okay, we're coming out this way. 5 pi over 6, I'm going to guess is going to be either a 2 or a negative 2. 2, and then if we do pi, we're back to a 4. So we've started here, we've come around, we've looped here, we're going to loop, and we're going to come up and loop here, and back down. Alright, that's why it's just pretty key for these rose petal ones. It's key to know the maximum values in 0. Okay, our zeros would have happened at everywhere that cosine of 2 theta equaled 0. So wherever 2 theta is, what's going to make cosine equal 0? Well, if cosine was pi over 2, that would have been 0. Or if 2 theta would have equaled 3 pi over 2 is where cosine is also 0. And we would have got pi over 4s. So we're going to be pretty much counting by pi over 4s. And then 3 pi over 4 from that one. And then you can keep going around the loop. 5 pi over 4 because it's going to happen twice. And then 7 pi over 4. So the odd pi over 4s are where we would have got our zeros. And then the pi over 2s are where we had our maximums at. So that can be helpful. And again, you can graph that out on your calculator to get help. Okay, several important types of graphs have equations that are similar in polar form to the ones in the rectangular form. For example, a circle, r equals 4 sine theta, from the example 1, has the more complicated rectangular equation, x squared plus y minus 2 squared equals 4, whereas it's much simpler in this format, r equals 4 sine theta. It's a shorter and simpler to graph or to write down, but maybe to graph it just from experience with rectangular ones, it's easier that way. Several other types of graphs that have simple polar equations are shown below. We've got limicones or limasones. I'm sure Cameron's having a field day with my pronunciations of the fancy characters. You can insert some snarky comment right there. So we got a plus or minus b cosine theta, or a plus or minus b sine theta. And a and b both are greater than 0. And depending on what the ratio here of a to b depends on if we have a inner loop, a cardioid, aka a heart, or just a little dimpled one. Remember our Tom Brady football? And then a convex one where it's just kind of a flattened out circle. It looks like it's going to be a circle and it just kind of flattens out. There's no dip in or point in or loop. It's just kind of flattens out, loses its curve. The fun ones are the rose curves. Okay, if it's just a times cosine n theta or a times sine of n theta, it's going to be a rose petal one. And if that multiplier on theta is odd, then it will be that many petals. So if it was like a 3 theta, you're going to have 3 petals. If it is even, it works out to be twice as many petals. So if we had a 4, you're going to actually end up having 8 petals. Here it was 5, so there's only going to be 5 petals. Here it was only 2, but doubles up to be 4 petals. Yeah, we're probably going to focus more on like the 2s and the 3s. I mean, if you get to like 5s or 4s and 5s, like this would have been a lot of loops to go through. Loop, 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 loop. Other special ones, we got circles. A times cosine theta is going to be a circle on the polar axis. A times sine of theta is going to be a circle on the pi over 2 axis. A lemniscate, or kind of like a figure 8 or an infinity sign. Okay, it's going to be tipped diagonally. It's r squared equals a squared sine of 2 theta. It's going to be tipped diagonally if it's a sine one. And this spot, this r value at the maximum is going to be your a. So if this was like 4, that would have been 2 squared. So this would be a 2, and that would be a 2. And then you kind of just do your figure 8. If it's a cosine one, it's going to be on the polar axis. And again, this is a squared. So if this was like a 9, your a would have been 3. So I'm 3 out this way, 3 out this way, and then kind of do your little infinity sign. All right, what else we got here? So now that I've looked at those, I can do some shortcuts. Okay, 3 cosine of 2 theta. So it's an even theta, so I know it's going to have 4 petals. All right, and it's going to be symmetric with respect to the x, or the polar axis. Okay, we can even graph it and get a quick picture of what it's going to look like. Three cosine 2 theta. So you can see it's like a 4-leaf clover, but vertically there. All right, and then our radius there is going to be a 3, and we were on the 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And we can go through and dot these out. Okay. Something like that. Just keep looping around. Okay. Again, maybe just to play it safe and a little bit of overkill, go ahead and plot out the top half and then reflect it over. Might be a good idea for like a beginner there, first time. We have r squared equals 4 cosine 2 theta. So the r squared is going to be a huge indicator that it might be a lemniscate. So if I bring that back, so we're looking at a cosine one, so it's going to be side to side, not the tipped one. A squared is, in this case, so this was 4, so my a is a 2. So we're just going to go 1, 2, 0, 1, 2. And it's just going to keep looping like that. All right. So there we go, guys. That is it for 10.8. It's a bit of a long one. Normally it would have been like a 2 or 3 day lesson. So this video is a little bit long, almost 40 minutes now. But you guys got 2 days here to work on that. And then I believe our next class is going to be review for your test. And then we'll utilize our Friday class time to take that test. All right, so let me know how you guys are doing. And we'll talk to you guys later. Thanks for watching.